Today, we are honored to have Assistant Professor Napat Rujeerapaiboon from the Department of Industrial Systems Engineering and Management. He completed his PhD in Risk Analytics and Optimization at EPFL. Some of his research interests includes data-driven optimization and risk analytics. Today, he will be sharing about operation research. Professor Napat, please.
Thank you. Okay, so good morning, everyone, and thank you very much for the IC team for the kind introduction of myself, right? So as they mentioned, right, so my name is Napat Rujeerapaiboon, right? I'm an assistant professor at NUS, right? And today, I would like to share you a little bit about the topic of linear optimization, right? With this kind of like the introductory topic to operation research in general, right? Even though the topic may seem to be a bit at the beginner level, right? But it turns out that this topic is very useful and heavily used in the industry, right? So that is why I'm sure that this is going to be useful for your case competition that will start later this month. Okay, so I'm starting to share my screen now. So I hope that you all can see my screen. If that is not the case, then please let me know the problem so that I can fix immediately. And otherwise, right, I would expect to start this workshop now, and this workshop should be about an hour, I believe. Okay, right. So first of all, right, before we getting into the technical contents, as well as for me to share some examples about the linear optimization problems, right? I would like to give a brief motivation first why we are interested in the mathematical concept that we call optimization. Okay. So you may ask, right, what is the optimization, right? And it turns out that optimization is actually a branch of mathematics or even applied mathematics that is heavily used by some people outside the mathematics domain as well, right? So that is why, for instance, right, in our engineering curriculum, optimization is one of the part of the topics that the students have to study as well. And outside engineering, right, optimization is also a topic that is heavily used in business analytics also. Okay, but at its core, right, optimization is somewhat of a branch of mathematics that involves several aspects altogether. Right, so first of all, we need to do something about mathematical modeling. And what it means by that is that since optimization is going to be used in real world, right, we need to collect the requirements from real world, right, as a verbal statement. And we need a mechanism somehow to transform this description of the problem into a mathematical formulation, right? And that is what I call mathematical modeling. Now, on top of mathematical modeling, right, you need to have some knowledge about algorithms if you want to solve the optimization problem that you have at hand efficiently, right? So this is why optimization is also a popular topic in computer science and computer engineering, as well as electrical engineering also. Now, some of you, when you formulate an optimization problem, right, you may have some unknown parameters on the optimization problem. And in order to model the unknown phenomena, right, you may also be required to use some knowledge from statistic and probabilistic domain also, right? But this is going to be a little bit outside of the scope of what we discussed today, right? Because what I would like to do is that I would like to focus on the first part about the mathematical modeling. I will touch a little bit about the last part on the algorithmic part, right? But not so deep about the statistic and the probabilistic model. Now, when you have an optimization problem, right, roughly speaking, right, the goal is that basically you want to solve a decision-making problem and you want to identify what is going to be a good solution to your decision-making problem. And decision-making problem can be anything, right? It can be a very simple, very trivial problem, such that you may want to plan a diet. You may want to come up with a diet plan to minimize the amount of calories intake, for instance, right? Such that you will still be healthy, right? So you need to consume enough amount of proteins. You still need to consume enough amount of fat. You need to still consume amount of vitamins and minerals, for instance, right? So this is one of the basic daily life optimization or decision-making problem that you may encounter. But on the other hand, right, the scale of the decision-making problem could also be very large as well, right? So not like the individualized in the diet problem anymore, but it could also a problem from the government perspective, right? So for instance, right now in Singapore, there's a news about GST hike, right? So from the government perspective, right, they may have an optimization problem that they solve already, right? And they say that this 2% hike is actually the most appropriate number, Okay, so decision-making problem could be anything, right? And now, right, since I say that we want to identify a good solution to a complex decision-making problem, right? We need also a criteria to measure, right, the goodness of the solution that you may have, right? What is going to be counted as good, what is going to be counted as bad, right? So that is why, right, over here in the last portion of the slide, right, I list some of the common objectives that people would like to achieve when they talk about decision-making problems. So for instance, right, if you are a business owner that you would like to sell some products, right, then the objective that may be of interest to you is that you may want to maximize the profit that you could earn, right? Again, if you are a government, right, maybe the profit is not your biggest concern, right, but you may want to minimize the cost of your operation, right? So this is another typical objective that you encounter in the OR studies. If you are a network engineer, right, you want to make your network to be available to as many possible people as you can, right? So that's roughly translate that you want to maximize the bandwidth of your network. If you are a financial investor, right, you may want to minimize the risk of your investment. And last but not least, right, if you are a project manager, right, then you may want to maximize the efficiency of your workforce. And at the same time, you may also want to minimize the completion time of your project as well. Right, so these are some of the typical objectives that will show up in your optimization problems. Right, and I hope that these are intuitive enough for us to understand and to appreciate the importance of the OR or the linear optimization studies. Okay. So now that we roughly understand what is a decision-making problem, right? The next thing that I would like to talk is about the mathematical programming or the mathematical optimization problems, right? Because as I mentioned before, right, after we gather the real-world requirements, right, we need to translate that into a mathematical language that people will universally understand, right? So here in this slide, right, basically what you see over here is kind of like the standard way that you would like to express your optimization problems. And there are going to be three main components of the optimization problem that I would like you to be aware of. Right, so first of all, right, since we are talking about decision-making problem over here, right, you will have some decisions, right, a single decision or multiple decisions that you have to make. Okay. So collectively, right, I will refer to all the decisions that you have to make by using a single vector x, right, that is going to be a vector in Rn, right? So in total here, I assume that you have n decision variables that you have to make, right? So this is going to be the first component of your optimization problem. Now, as previously mentioned in the last slide, right, the objective of the decision-making problem is to maximize or to minimize something, right? The cost minimization or the profit maximization problem is particularly of a bigger interest, right? So as a general concept, right, I will say that I have basically an objective function, right? And I use the notation f to denote my objective function. And this is going to be something that I would like to minimize or I would like to maximize. So here in this optimization problem, right, I basically assumes that I want to maximize, right, the function f that depends on the decisions that you will make x, right? And you can think of this f as a cost function in particular, right? So this is a requirement that we see already, right? So now somewhat of a new requirement that I haven't talked about before is basically the feasible set of the optimization problem, right? Because here we have that the decision variables x is a vector in Rn, right? But it's not like that this x could be any vector, right? It couldn't be just any arbitrary vector, right? There are typically some requirements that you need to adhere with, right? So for instance, right, if you talk about the production problem, right, if you want to produce something to sell, right, the decision variables may be the amount of the products that you would like to produce, right? And some of the constraints that will determine the feasible set is that the amount that you have to produce is basically have to be non-negative number, right? So that's one of the naive requirements that you can think of. Now, just to give you a more realistic example, right? I work also in an energy sector, so many times, right, I would like to refer to the electricity production problem, especially by relocating the water in the system of reservoirs. Right? So imagine that you live in a country that is unfortunately potentially not going to be Singapore, right? Because when we talk about reservoirs, then we usually refer to those that are in the high mountains, right? And we probably don't have too many in Singapore over here. But let's suppose that we have some high mountains, right? And basically you can have multiple reservoirs within the mountains, right? Some of the reservoirs, right, may be located in the higher level of the mountains, right? So maybe 300 meters above the sea level, right? So this is, oh, sorry. This could be one of the picture of the reservoirs, right? So the reservoir has some water inside, right? Right. So this is the upstream reservoir. But on top of this, right, you may also have, say, the middle level reservoir, right, that is located at the medium level of the mountain. And you may also have some low level reservoirs, right, which is basically closer to the village downstream, right? So these reservoirs, right, usually will be connected to one another. And what it means by that is that there is actually a waterway that can connect multiple reservoirs together. So here from the top reservoir, right, according to the arrow over here, it means that you can release some of the water from upstream to the downstream reservoir, right? You can also release the water from the medium level reservoir to the low level reservoir as well, right? So you could think of the amount of water that you would like to release downstream by saying that this is a decision variable G1 that you may have, and this is the amount of water that you release downstream here is G2, right? Now, besides releasing the water downstream, right, you may also have a possibility to pump the water upstream as well, right? Because maybe, right, you like the water in the upstream level, right, but you may have too much water in the medium or in the lower levels, right? So in this case, right, you may have a possibility to pump the water up, right? And let's say that I would like to denote the amount of the water that you would like to pump up by these variables P1 and P2, right? So in this case, right, if I want to operate this system of reservoirs, right, so that means that I have the control over the value of G1, G2, and P1 and P2, right? So basically my decisions variable over here, right, would be the vector of G1, G2, P1, and P2, right? Since here is the example that I have multiple decisions that I could make. Some of the constraints that I have in these optimization problems that will determine the feasible set, as I mentioned before, right, is that these G1, G2, P1, and P2, right, needs to be a non-negative numbers. Now, on top of this, right, I may also have some other constraint as well, right? Because for instance, right, G1, right, G1 cannot be too large actually, because if I have a too large G1, then it means that I release the water downstream too much, and that could cause the flood downstream, right? So they will have too much water in the village, right? And this is something that you want to avoid, right? So typically, right, there would be some constraints that say that the G1 needs to be smaller than some threshold numbers, which I indicate by G bar 1. G2 must also be smaller than by some other numbers than G bar 2. Now, besides all these constraints that I mentioned, right, there may also some sort of other constraint that you can think of for this system of reservoir as well. So for example, right, typically, if the mountain area is beautiful, right? So imagine that if you travel to Switzerland, to Austria, or to Germany, right? From the regulator perspective, there usually a requirement that the amount of water in the reservoirs needs to be high enough, right? Because no tourist is going to go there to the mountains and want to see the empty reservoirs, right? So in order to attract the tourists, right, you need to have a constraint that say that the water level, right, needs to be something like 80% full, for instance, right? To make sure that it's beautiful enough for us to attract the tourists, right? So all of these examples of the constraint, right, putting together, right, then this will be the description of the feasible set, right? It's basically the scope of the variables X that it could take. Okay. So three components of the mathematical optimization problem, right? The decision variables, the objective function, and the feasible set. Now, given just this mathematical description of the problem that you see over here, right, one could envision that the decision-making problem that we have can be highly technical, highly mathematical, right? Especially if the constraints are highly nonlinear and if the objective function is also a highly nonlinear function as well, right? But what we are going to focus on today is just a small subclass of the overall optimization problems actually. So this is the name of the object that we are going to be interested in, which I think many of you are familiar from the high school curriculum already, right? So we are going to just talk about the linear programming problem. And what it means is that the objective function f that we defined previously needs to be a linear function. Okay. On top of this, all of the constraints that we come up to define the feasible set, right, needs to also be linear as well. It could be linear equality constraints, or it could be linear inequality constraints, right? We are going to see some of the examples of both equalities and inequalities constraint later. Now, as we are aware of, right, linear functions are actually a very naive functions that you could think of, right? And that give rise to the linear optimization problems, right? But it turns out that even though the linear optimization models are just a small subclass of overall mathematical optimization problems, it turns out that this is highly influential, highly powerful already. Because according to the survey, right, many of the famous firms in the US, right, 85% of them, right, have been reportedly to benefit from the use of the linear programming models, right? So if you can use linear programming problem efficiently, right, then it means that this is going to be very beneficial to the business that you would like to work with later on. Okay. From the experience of myself as well, right, when I mentioned about the energy problems sector that I worked with before, right, they also told me that just by simply using a linear programming problem, they can increase the profitability of their company by at least 10 million euro in a year. Okay, so that's how powerful this linear optimization problem is. So next, what we would like to do, right, is that I'm going to talk a little bit about an example problems of a linear programming problems, right, so that we are a little bit more familiar with how to solve a linear optimization problems. So here what we have, right, is that basically we are to focus on what we call a manufacturing problems. And what it means by that, we have, say, a company, right, that is capable of producing some products in order to sell. Now, the question says that there are two types of the products that this manufacturer can produce, right? The first type of the product is the acid A, and the second type of the product is the caustic C, right? These are the products that the company want to sell, right? But to produce A and C, right, you need to have some raw ingredients, right? You need to have some raw materials, right? So that's why the questions also give you some specification about the production requirements of A and C. In particular, right, to produce A and C, you will be required to have come up with the raw materials which are given by the raw material X and the raw material Y. So the question says that for 1 unit of A, right, you need 2 units of the raw material X and you need 1 unit of the raw materials Y, right? So this is what the question suggests, right? So let me just write this down, right? So if you want to produce 2 of X, sorry, if you want to produce 1 unit of A, right, you want to have 2 units of X and 1 unit of Y, right, in order to produce 1 unit of A, right? So that corresponds to this bullet point over here. Now for the second bullet point, it says that in order to produce 1 unit of the caustic C, right, you are also required to have 1 unit of X as well as 3 units of Y in order to produce 1 unit of the caustic C, right? So these are the translations of the real world requirements into somewhat of a more mathematical way, right? So now if I suppose that I don't just want to produce 1 unit of A, but I want to produce X1 unit of A, and I also don't want to produce just 1 unit of C, but I want to produce X2 unit of C, right? So based on this requirement, right, what I have is that I need to have in total, right, 2X1 plus X2 unit of the raw material capital X, as well as I need to have X1 plus 3X2 unit of the raw materials Y, right, in order for me to be capable of producing X1 unit of A as well as X2 units of C, right? So if I have X1 and X2 over here, right, then this is the amount of X and this is the amount of Y that I have, right? But the question also says that I don't even have an infinite amount of this either, right? Because these X and Y, right, these raw materials needs to be purchased from somewhere, right? It needs to be supplied from the supplier. And the question also says that we have a limited supply over here. So here for the raw material X, right, we can acquire only 11 pounds in a week. And for the raw material Y, we can only acquire 18 pounds of the raw material Y in a week also. The question also says that the selling price of the product A, right, the acid, is 1,000 pounds per ton. And the selling price for the caustic C is also about 1,000 pounds per ton, right? So the product A and the product C are equally profitable, right? Now, on top of all of this, right, we also have the result from the market research team to suggest that no more than 4 tons of A can be sold in a week, right? So all of these are the requirements that you gather, right? And we are going to suppose that the objective of the manufacturer is to maximize the revenues, right? And in order to maximize the revenues, right, since we have the equal selling price for A and C, right, then basically this is just to say that we would like to produce as much as possible. Okay, so all of these putting together, right, as I mentioned before, right, we are going to introduce the decision variable x1 and x2, right? So these are the decision variables corresponding to the amount of A that you would like to produce and the amount of C that you would like to produce respectively, right? So this is the first component of the mathematical optimization problem. On top of this, right, you will also have an objective function, which is the weekly profit, right? As I mentioned before, right, since to maximize the weekly profit is basically the same as maximizing the total amount that you can produce, right? Then basically this f function is going to be just given by x1 plus x2, especially since because A and C have the equal selling price, right? And now in terms of the feasible set, right? So it's a scope of the values that x1, x2 can take, right? And we know just from the problem description, right? x1 and x2 cannot just take any arbitrary values. First of all, x1 cannot be negative. Second of all, x2 cannot be negative, right? But it still not means that all positive amounts will be okay, right? Because let's suppose that if you have a decision vector x, where x1 is equal to 27, right? If you want to produce 27 units of A, right? According to the problem requirements, right, you would need twice of this amount of the raw materials X, right? Which is 54, right? But 54 already exceeds the weekly supply that you have, right? For the raw material X, which is about 11, I think, right? So you cannot have X1 to be equal to 27 either, even though it's positive, right? But it's still not allowed. Okay. So in the next step, right, what I would like to do, right, is that I would like to visualize this problem by using this two-dimensional Euclidean plane. And the reason that we can do this is because we only have two decision variables in this example, right? We already have x1 and x2, right? But you could imagine that for a more complex problem where you may have hundreds or even millions decision variables, right? Then it may be more difficult to come up with a visualization of your optimization problems. But for this problem, you still can, right? So here, the horizontal axis will represent the value of x1, and the vertical axis will represent the value of x2. Okay. So now in terms of the profit function, right, as we mentioned before, right, we know that our profit function is basically the summation of x1 and x2, right? And basically we want this summation to be as large as possible in order for our profit to be maximized, right? So what I draw over here is actually a collection of different lines that correspond to different values of the objective function, right? So for example, right, if I take a look at this line that I indicate by the value 0 over here, this is basically the lines that contains all of the x values, right, such that my profit f would be equal to 0, right? So basically what it means is that this is the line where my f1, x2, which is the summation of the two things, right, is actually equal to 0, right? That is why it is a line that passes to the origin where x1 and x2 is equal to 0. Right? So the other lines that you see over here, right, will correspond to the set of the decision variables, right, that will give you the different objective values, right? So for instance, right, this line over here will contains all of the value of x1 and x2, right, such that the profit function f, right, would become 1, right? So on and so forth, right? So I have a line that corresponds to the profit function of 2. I have a line that corresponds to the profit function of 3, right? 4, 5, 6, 7, 8, 9, so on and so forth, right? But now the idea is that f is our profit function, right? So we want our f to be as large as possible, right? So that means that if we are allowed to do so, right, what we would like to do is that we would like to go into the northeast direction, right? We would like to go into this northeast direction, which is the direction of the gradient, right? Because as long as we continue to go in this way, then what you could see from the visualization is that the profit will increase, right? So you would like to go into the northeast direction over here, okay? So that's the visualization of the objective function. So now in terms of the constraint, right? So we have several constraints over here, right? So first of all, some trivial physical constraints, which is to say that the amount that you can produce for either A and C, right? It needs to be a non-negative number. So we have a requirement that X1 needs to be a non-negative number. And this is basically give rise to the yellow region that you see over here. Similarly, you also have another constraint that say that X2 must also be larger than or equal to 0 as well. And this will give rise to another yellow region over here, right? These are some of the trivial constraints, right, that will define your feasible set, but they are not the only ones, right? Because we also have some other constraints that we have also. Now we have already made an argument before that in order to produce X1 unit of A and X2 unit of the caustic C, you would require the amount of the raw material X, which is given by 2X1 plus X2, right? This is according to the requirement that you gather from the problem. But you also have a specification of the problem that the amount of the raw material X that is provided to your company is going to be at most 11, right? So all in all, that means that you cannot produce A and C, right, to be any arbitrarily large number, right? You need to have this constraint that says that 2X1 plus X2 must be smaller than or equal to 11. So now what I do over here, right, is that basically, right, I first draw the line that corresponds to the equation 2X1 plus X2 to be equal to 11 first, right? And now after I draw this line, right, then basically this line will divide my whole Euclidean space into two half space. One half space will correspond to 2X1 plus X2 smaller than 11, and the other half space corresponds to the region where 2X1 plus X2 to be greater than 11. But since over here, right, we have less than or equal to inequality constraints, so that means that the area of interest to us is going to be this yellow region over here, which is the area in the bottom left, right? In a way, right, this is because we cannot produce X1 to be too large and we cannot produce X2 to be too large, right? So that's why we need to pick this yellow region over here. So this is the constraints on the amount of the raw materials X that you have. On top of this, right, you will also have a similar constraints, a similar visualization for the raw material Y as well. Because in order to produce X1 unit of A and X2 unit of C, right, you need a certain amount of the raw material Y, which is given by this expression X1 plus Tx2. But the question also says that at most, you will have 18 pounds of these raw materials, right? So similarly, you have also these similar smaller than or equal to inequality constraints that you need to incorporate into your optimization problems, right? Again, I make a visualization, right? So first I draw the equality version of this constraint, which is going to be just a line. This line will divide my feasible set into two half spaces, right? Corresponding to the two different directions of the inequality symbols. And then I pick this one, right? The yellow region over here, which corresponds to the smaller than or equal to inequality constraints. Okay, so this is the area that I pick up. Now, last but not least, right, we also have another requirement to the manufacturing problem, because we also have a market research team that help us. And the market research team tells us that we will never be able to sell more than 4 units of the acid A, right? If we cannot sell more than 4 units of A, then it doesn't make any sense for us to produce more than 4 units, right? Because otherwise there will be some leftover for sure, right? So that means that the other constraints that we can incorporate into our optimization problem is basically the constraints that say that X1 must be smaller than or equal to 4, right? So in other words, right, we are going to be interested in the left-hand side of this visible region over here. So all in all, right, you see that each of the constraints, right, each of the requirements that you have in your optimization problem will give rise to one yellow region, which is basically one half space. Now, we are going to be interested in the solutions that specify all of the requirements at the same time, right? So in other words, right, we are going to have to make an intersection of all of these, right? So when we make an intersection of all of these, right, we just have a really nice compact feasible set that you have for this optimization problem. And the shape of this and the shape of the feasible set is given by this pentagon over here. Now, a special characteristic of this pentagon or even triangle, rectangle, or hexagon whatsoever, right, is that it has some vertices, right? So the vertices of this feasible set, right, I give the name, right? So I have the point O that corresponds to the first vertex of the feasible set. And this vertex, right, is basically given by the coordinates 0 and 0. There are some other vertices that appear in the optimization problem as well. Namely, we have this point P, this point Q, this point R, and this point S, right? So in total, since we have a pentagon feasible set, right, we have the 5 vertices of the feasible set that we can enumerate, right? So these are some special characteristics of the linear program, particularly for these manufacturing problems. So whenever you have a linear optimization problems, whenever you have a linear objective functions, and whenever you have linear constraints, then the feasible set will just be something like this, right? A typical shape that you can think of, right? Triangle, rectangle, hexagon, pentagon, so on and so forth, right? In a mathematical language, the feasible set of this type is what we call a convex polygon. And this is basically the simplest shape that we can hope to work with, right? There wouldn't be anything that is more simple than this. Now, the vertices of the pentagon that we saw previously, right? Some people will call it the vertices of the feasible set. And the idea is that it would be the same as the notion of the extreme points, right? So these two definitions are more or less the same thing, right? So whenever you study about the linear optimization problems, people like to use the word vertex and the word extreme points interchangeably, right? And here, right, in order for you to determine the coordinate of all of the extreme points, O, P, Q, R, and S, right? Basically, what you have to do, right, is that you have to solve a system of equations, right? So for instance, if you want to determine this index Q, right, the coordinate of Q, right, we know that it belongs to this line and it belongs to this line, right? So we know that it must specify the requirement that 2x1 plus x2 is equal to 11. At the same time, it also needs to specify another equality constraints, which is x1 plus 3x2 to be equals to 18, right? If you solve this system of 2 unknowns and 2 equations, right, then you will get the value of x1 and x2, where x1 must be equal to 3 and x2 must be equal to 5. And this is basically the coordinate of the point Q, right? And you can do this to enumerate all of the coordinates that you find in this feasible set over here, right? So besides the visualizations, right, we can also put this into a mathematical framework, right, so that it can be universally understood by any people who know a little bit about optimization problems, right? So as we know, right, our objective function that we want to minimize, right, is basically just the summation of x1 and x2, right? And we want to choose x1 and x2 subject to several constraints that we just write down, right? So basically we have a bunch of inequality constraints we need to specify. Right? Now, putting all together, right, we have the visualization of the objective function, right, that is given by these different lines already. And also, we also have the visualization of the feasible set, which is given by the yellow region, right? If I put things together, right, then this is going to be the final visualization that I have, right? So basically, in view of the feasibility, right, you have to be within the yellow region, right? Because this is the scope of your feasible set, right? But from the objective functions perspective, right, you want to go into the northeast direction as much as you can, right? Because as long as you go into the northeast direction, right, then you will acquire more profit. Okay. But now, right, you cannot go to the northeast direction indefinitely, right? Because if you continue in the northeast direction, right, at some point you will be out of the yellow region, right? So that means that that particular decision, right, is not feasible for you, right? So that is why, right, you have to respect the yellow region that you have, but you want to go into the northeast direction as far as possible. And you can see that the best decision that you can come off is going to be this point Q over here, right? So this point Q, right, still belongs to the yellow feasible region, but at the same time, right, it is the most northeast that you can go to already, right? Because if you want to go to the northeast a little bit further, you will step out of the yellow region already, right? So that means that we managed to solve this linear optimization problem already just by using this graphical representation of your linear optimization problem. And you know that the optimization, so you know that the optimal decisions for this problem is going to be given by the coordinate Q that we derived before, right? So that means that the optimal value for x1 is going to be given by 3, and the optimal value for x2 is going to be given by 5, I think, right? The way that we derived it before. Okay, so that's actually the whole idea, right? For us to solve a linear optimization problem already, and maybe you have studied this already, right? But in a more deeper context, right? This is actually quite an inefficient way of solving an optimization problems, right? Because first of all, right, if you want to solve the problem this way, what you have to do, right, is that you need to draw, and then you need to determine all of the possible vertices of the feasible set, right? And then you need to try to identify what is the vertex point, right? That is the most favorable in view of the objective functions. There are a couple of issues with this approach, right? But most importantly, right, the most significant drawback of this approach is that the number of the vertices that you have to enumerate, right? It could be very, very large, right? Typically, this will go with exponentially with the dimensions of the problems. So for instance, right, if you have, say, 100 constraints, right, you may have something of like 10,000 vertices that you need to enumerate. And this is going to be very difficult to do it by hand. So that's why there are some computer scientists, there are some mathematicians who work together to come up with an algorithm that will allow you to solve the linear program more efficiently. And there are several variants of the algorithm actually, right? So one algorithm is named a simplex algorithm, and the other famous algorithm is named interior point algorithm, right? So if you study the OR a little bit deeper, then these are the names that you can expect to hear, right? From the computational perspective though, right, nowadays, right, you may not be expected to develop these algorithms by yourself because many people have done it already, right? So there is actually a toolbox that you can already use within the Microsoft Excel, for instance, or if you're familiar with the Python programming language, then there's also a software toolbox that you can use to solve an optimization problem there also. Okay. So now, right, just to give you a little bit more flavor of the linear optimization problems, right? What I would like to do next is that I would like to give you a couple of more examples of a linear optimization problems. That examples that you can get yourself familiar with, right? The next example that I would like to look at is what we call the work scheduling problem, right? So the idea of the work scheduling problem is that you would like to make an arrangement of the employees within your workforce. Okay, so just to give a little bit more context to the work scheduling problem that we would like to take a look at over here, right? Let's suppose that in the future you are a manager of a sync post branch, right? So what you want to do is that you want to come up with an arrangement of the postmen, right? The post officers that they will work for you. Now, on the different days of the week, right, you may have a different demands, right? Maybe people like to send posts on Monday, for instance, right, in relation to, say, Friday, right? So different days of the weeks, right, we have different requirements. And I will denote these different requirements by E1, E2 to E7, okay? So you can think of day 1 as Monday, and you can think of day 2 as Tuesday, so on and so forth, right? And day 7 is going to be your Sunday, Okay. So on Monday, right, on day one, you will be required to have a certain number of postmen to work for you. And this number is going to be given by E1, right? So this is like the minimum number of employees that you need to have available at hand, right? So this is going to be the number of employees that you need to have at hand on Monday. E2 is going to be the number of employees that you need to have available on Tuesday. So on and so forth until E7, right? This is going to be the number of employees that you need to have available at hand on Sunday. Now, even though these are mathematical symbols, right, I would like to highlight that these are not decision variables, right? Because these requirements, right, are not something that you have to control over, right? Somebody will say this to you, right? That on Monday, I need to have at least 10 employees. On Tuesday, I need to have at least 12 employees, right? This is not something that you have the control over, so they are not the decision variables in your optimization problem. But then what do you have control over, right? You have the control over the postmen or the employees that you will hire on different days of the week, right? But now, in order to make this problem very realistic, right, there would be some requirements that you need to adhere in order to respect the physical and the mental health of the employees. So in particular, each employee, right, can work consecutively for 5 days in a week. And then after these 5 days, right, then they need to have 2 days off, right, in order to rest. Okay. So let's say that I have X1 employees who will start working for me starting from Monday. So these X1 employees will not just work for me on Monday, but they will also work for me on Tuesday, Wednesday, Thursday, and Friday also. Right? And then these people, right, these X1 people will take Saturday and Sunday off. Now, similarly, right, let's say that I have X4 employees who will work from me starting on Thursday. So these X4 people will have to work on Thursday, Friday, also Saturday, Sunday, and also Monday, but they will take Tuesday and Wednesday off, right? So this is their work cycles, right? So basically, right, the aim of you, right, the aim of the SyncPost branch is that they want to trim down the size of the workforce as much as possible, right? So they would like to have a minimum number of postmen, right? They would like to have a minimum number of employees. And here in the table, right, is basically the visualization of what happened, right? Let's say that I will have X1 number of people who start working with me on Monday, right? As I mentioned before, right? These X1 people will not just work for me on Monday, but they will continue on Tuesday, they will continue to Wednesday, they will continue to Thursday, and they will continue to Friday also. Similarly, right, I will have a decision variable X2 in my problem to denote the number of employees who will start working for me starting from Tuesday. So these people, right, they will work on Tuesday, they will work on Wednesday, they will work on Thursday, Friday, and Saturday, and eventually they will take Sunday and Monday off, right? So basically from what you can see over here, right, you will have X1 as your decision variables, X2 as your decision variables, X3, X4, X5, X6, and X7, right? So these are going to be the decision variables that you have in your optimization problem. And this is basically the first component that you need to specify in your optimization problem. Second, right, we need to also specify the objective function that you would like to have in this optimization problem as well. Now, as I mentioned before, right, the goal is to trim down the workforce as much as we can, right? So that means that we would like to minimize the total number of employees, right? So our objective of this optimization problem is that we want to minimize the summation of all these x. Right? So this is going to be your objective functions. So now what is going to be the feasible set, right? What are the requirements that you have about these decision variables, right? So in terms of feasible set, right, at the very least, you have some trivial physical constraints to say that all of these decision variables which denote the number of employees to be hired on a specific day right? This needs to be non-negative, right? So I know that x1 needs to be non-negative, x2 needs to be non-negative, so on and so forth, right? Until x7, right? This needs to be non-negative. But besides this, right, I will also have some other constraints, right, which is basically the minimum requirements on the number of employees that I need to have on different days. So for instance, right, if I take a look on Monday, right, which is basically day 1, right, the total number that I have over here, right, is going to be given by x1 plus x4 plus x5 plus x6 plus x7. Right? This is the total number of employees that you will have on Monday, right? And this needs to exceed the minimum requirement, which we discussed on the first bullet point, right? The requirement is basically this needs to be greater than E1, right? Similarly, you can come up with the constraints on Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday, right? Let me just give you another example, right? If you focus on Tuesday, right, then basically the total number of employees that you will have on Tuesday is basically x1 plus x2 plus x5 plus x6 plus x7. And in aggregation, right, combined, right, they need to exceed the minimum requirement, which is basically E2, right? It's a requirement on Tuesday, which is a day 2 of the week. Okay. So all in all, right, basically, if you want to write down your big optimization problems, then this is what you have, right? Again, right, you have the decision variables x1 to x7, and you want to minimize the size of your workforce, right? So that's why the objective function is basically written down as a summation of x1 to x7. The constraints of your optimization problem is that all of the x needs to be non-negative, and that the number of employees that you have for each day of the week needs to exceed the minimum requirement, right? So this is the requirement on Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday, right? Where E1 to E7s, again, are not the decision variables, but these are the numbers that must be provided to you. Okay. So now, last but not least, right, I would like to discuss another example to give more context, to give more the idea of how to utilize the linear programming problems, right? This example is a little bit more complex to the previous two, right? It's about air traffic control. So suppose that you have a sequence of airplanes that needs to arrive in order, right? So you have a sequence already that airplane 1 needs to arrive first, airplane 2 needs to arrive second, airplane 3 needs to arrive the third, right? And in total, you have capital N airplanes in total, right? So on top of this specific order that you need to respect, right? Actually, you also need to have a requirement that the arrival time of the N airplane, right, needs to be between AN and BN, right? So AN is the earliest arrival time and BN is the latest arrival time, right? So these are the problem requirements. Again, A and BN are not decision variables, but they are the numbers that are given to you, right? So maybe you want a plane from Thailand to arrive in Bangkok between 2 p.m. and 3 p.m. So in this case, the A would be 2 p.m. and the B would be 3 p.m. Now, for safety reasons, right, you don't want two planes to arrive in a close proximity, right? For example, right, you don't want the first plane to arrive now and the second plane to arrive just 5 minutes later, right? Because if two planes arrive almost at the same time, right, then that will give you the safety concern, right? So that is why you want to maximize the gap between the two consecutive arrival times, right? The gap between the two consecutive arrival times. Okay. So now if you want to formulate this as an optimization problems, right? So first of all, I will indicate my decision variables, which I will denote by T1 as the first arrival time, T2 as the second arrival time, as well as T capital N, this is going to be the last arrival time, right? According to the requirement in the first bullet point, I will have the requirement that my T1, right, the first arrival needs to be in the interval between A1 and B1. The second arrival time needs to be in the intervals between A2 and B2, right? So I will have that requirement, right? So on and so forth, right? And we also have the requirement that AN must be smaller than Tn must be smaller than Bn, right? So these are some of the constraints that I will have in my optimization problems. Okay. Now on top of these, right, I also say that the airplanes need to arrive in the specific order, right? So that means that I will have some other constraints that say that T1 must be smaller than T2, T2 must be smaller than T3, so on and so forth, right? And these together, right, must be smaller than Tn, which is the latest arrival time. Okay. So the decision variables of this problem are clear, right? The constraints of these optimization problems are also clear as well. But now when we talk about the objective function, right? And basically we say that we want to make the gap between the consecutive arrival times to be as large as possible, right? But let me just draw the timeline over here, right? So let's say that this is T1, this is T2, right? Second arrival time, this is 3, so on and so forth until Tn, right? You see that there's actually a lot of inter-arrival times, right? The gap, right? There are many of them. For example, right? You don't want the gap between T1 and T2 to be small, right? You want T1, you want T2 minus T1 to be large. You want also the gap between T3 and T2 to be large as well, right? For safety reasons, right? And eventually, right? The gap between T capital N and T at capital N minus 1 needs to also be large as well, right? So you want actually all of these numbers to be large at the same time. But how do you want to do this, right? So in order to do this, right, basically, right, what I want to say is that if you want to formulate these as some precise mathematical optimization problems, right, you want to specify your objective function. But the objective function that I would like to propose to you, right, you have the right to agree or disagree with me, but I think this will be the objective function that makes sense to me, is that basically I want to maximize the smallest arrival time. Because if my smallest arrival time, if the smallest arrival time, inter-arrival time is large, right? If the smallest gap is also big, then that means that all the gaps must also be big as well, right? So what I would like to propose is that I would like to maximize the smallest number between T2 minus T1, T3 minus T2, so on and so forth until T capital N minus T capital N minus 1, right? So I want this smallest gap to be large, right? So I want to maximize this objective function. Okay. Now there is a technical problem over here, especially if you want to use Excel or to use Python to solve this optimization problem. Because the objective function that we have over here, which is the smallest arrival time, is actually not a linear function anymore. It is not a linear function because you have the presence of this minimization operator inside as well, right? So what do we do then, right? How do we get around this problem? So in order to get around this problem, right, basically the trick that I will use is that I will introduce a new decision variable. It doesn't have a physical meaning, but it will just help me technically, right? So I will introduce a new decision variable delta to denote the value of the objective function over here, right? So in other words, right, I will have a new optimization problem where I will maximize over the delta, and when delta is defined as the smallest inter-arrival time, right? So this is going to be the relationship between delta and t that I need to incorporate. But then the problem is not over, right? Because now the objective is linear, because it's just delta, but the constraints turns out to be non-linear this time, right? Because the minimization that you impose there, right, used to be in the objective function, now it just moved to the constraint instead, right? So the non-linearity is still there within this optimization problem. So the next trick that I want to do is that basically I want to say that I can reimpose this constraint from an equality constraint to become an inequality constraint instead, right? So I replace the equality sign by the smaller or equal to inequality sign. But how can I do that, right? If I do that, do I change the problem? Obviously, I change the problem, right? Because I change the constraints. But in terms of the optimal solution, it turns out that this doesn't really matter. It doesn't matter because in view of the objective, right? You want to choose the delta to be as large as you can. And the constraint that I have over here, right, is basically the load upper bound that you have on delta, right? And if you want the delta to be as large as you can, right, then basically at optimality, right, the delta will be equal to the minimum expression that you see on the right-hand side still, right? So that's why it doesn't really matter if you have an equality constraint or if you have an inequality constraint. But then the benefit of having the inequality constraint on top of the equality constraint is that now this constraint would read that delta would be smaller than the smallest gap, right? But that is the same as saying that this delta must be smaller than each of the individual gap, right? That's what I can say. So basically, right, instead of having these non-linear inequality constraints, like I can write down the constraint as delta must be smaller than T2 minus T1, delta must be smaller than T3 minus T2, so on and so forth up until delta must be smaller than T capital N minus T at capital N minus 1. And then once we have these new formulations of the problem with both T and delta as our decision variables, then in this new formulation, it turns out that everything becomes linear now, right? Because we no longer have this annoying minimization anymore, right? If we have this annoying minimization, then the problem is not linear and you cannot do too many things about it. But in the new formulation with the artificial auxiliary decision variable delta, then it turns out that you get an equivalent linear formulation that you could quickly implement in Excel or in Python. Okay, so that would be the summary of what I would like to tell you today, right? So basically, I just want to introduce you to this concept of linear optimization problems, how to visualize it, right? And based on the visualization, how can we solve it, right? And that's bring us to the introductory algorithms that we can use to solve a linear optimization problems, like simplex algorithm or interior points algorithm. I also introduced you to a couple of examples that you see today, right? Especially the last example, right? Even if you have a non-linear problems, then it doesn't mean that you have to give up, because by modifying, by massaging the problem in the right way, then you can also obtain an equivalent linear optimization formulation that you can work with. Okay, so that will be all today. So I would hand over back to the team from the ISC department in case that they have some subsequent activities to do later on.